Okay, we're getting started now. Hello, online people. Oh, everybody say hello. Everybody wave, come on. All right. Okay, so today I'm going to review briefly the online surveys you all took in the middle of the semester. We also have right now the official survey. So let me turn the microphone on here. Testing. Oh, and could someone online post a question saying that you can hear us, just to make sure sound is working. We also have ongoing right now the official Georgia Tech class survey. And our dean, well, everybody thinks it's real important, so I'd appreciate it if you would take that online survey. If you do take it, you're eligible for an iPad, even if you're not a COC student. So that should inspire you. I guess there's probably 1,000, 2,000 people who take the survey, so it's better than the lottery, anyways. The chance of winning. Okay, they can hear us. Great. So let me start by going through the surveys. So this was about let's see, late September when we did this. So opinions may have changed since we took the survey. But let's see. I just want to make sure I have on the left here what the on-campus students said, and on the right is what the off-campus students said. So we'll look at each factor. It's interesting to see if there's differences. Anyways, class procedures are clear and well planned. 3% of the off-campus students strongly disagreed with that. That's interesting. Anyways, that's fine. Anyways, overall, about 4.1 for off-campus and 4.3 for on-campus. Of course, we like to see 5s there. I don't know what this question is about. This class provided a good transition from material covered in previous classes. This class is not meant to be any kind of transition. It's just supposed to slap you in the face with new information. So anyways, I'm surprised. I don't know what people were thinking we were transitioning from, but anyways, 4.1 on campus, 3.9 off campus. The instructors' presentations are helpful in understanding the subject matter. So glad to see good scores on there, 4.5 and 4.51. The instructor has stimulated my interest in this subject, 4.4, 4.4, that's great. The instructor has responded clearly to questions in class, 4.59 and 4.46. So those are all good. The instructor seems interested in the subject and appears, I only appear interested in teaching it. So we line this up. So good scores on that. Higher score online. So it seems like I appear more interested online than in person. So that's cool. The instructor appears to be interested in my success. So this one is interesting in that the on-campus students gave me a lower score than the off-campus students. But anyways, I certainly am interested in your success. The classroom provides a respectful environment that supports learning. For OMS students, consider environment to mean the online tools and present. Yeah, I don't know. It depends on where you're sitting when you're watching my course. Like if you're at a rock concert, I don't think that's as good as like Starbucks. But anyways, 4.43. So one person strongly disagreed with that on campus. 3 people strongly disagreed with it off campus. I suppose, well, I'm guessing that there's one person on campus that just strongly disagreed with everything. There's always somebody like that. Okay. Okay, next one worth looking at. My impression so far is this class is highly effective. So still above 4, which is good there, but more people online. Well, keep in mind that there's a lot of people online, but several people don't feel that. Let me skip down. So this one is a tough one, and I was curious how people would score it, because so the instructor utilizes learning techniques that require students to talk and engage in the class. So for online people, that can only mean that you engage on Piazza, say. And I have to admit that in campus here, I don't require you to talk and engage in the class. I'm not sure that's a good thing, so maybe that's why I don't do it. The instructor limits the amount of lecturing in favor of more student activity. So below 4.0 on that. Okay. So the text answers, I'm going to go through them myself a little bit later, and you know, kind of give you a synopsis of the good, the bad, and the ugly there. But we'll just go through the sort of quantitative ones here. So in terms of pace of the class, you know, in both cases, the mode and the median is just about right, with a slight shift towards too slow. Usually, so in the past when I've done the survey at the beginning of the course and at the end of the course, it shifts the other way towards the end. So just curious of the people in the room, who thinks the pace is too fast? Nobody? Really? Okay. Who thinks it's too slow? I mean, okay, I'm not, okay, oh, I saw somebody raise a hand. Okay, brave man. Okay, cool. I'm fine, I can take it. All right, who thinks it's just right? A lot of people? Okay, all right, that's good to hear. All right. I'm reviewing this in front of you, so I'm looking at these responses for the first time now myself, but you know, I want you to know it matters. Anyways, these are number of hours per week people spend in the class: 4, 8, 10, 9, 4, 10, online 20, 8, 20, 15. So a lot broader range of numbers of hours. 2 number of hours online. I wish they would just summarize that and give me a mean. But anyways, of course, there's a wider variation online. When I'm in class, I often feel excited, distracted, I wonder what that comes from. Okay, I'm glad to see interested is up there. Higher portion of people interested online. I wonder, if you're participating in the class online, that's pretty much all you're doing. Whereas if you're in class here with your laptop, you're also surfing the web. So those must be the confused people. Confident. Anyways, it's interesting that these all line up pretty similarly. Okay. Looking for more quantitative things here. Okay, that's it for quantitative stuff. I'll take a look through the written responses, and I'll post that somewhere so you all can take a look. Okay, so the next, let me see if there's anybody got any questions about that. Please do the official Georgia Tech CIOS survey. One thing you should know that I don't know if everybody knows is the numbers go to the school chair and the dean, but the written responses only go to the professor. So if you write something like, Balch is so lousy, you should fire him, nobody sees that but me. And I usually don't voluntarily save that or share that then with the dean. So as you write those things, just think about what you want to tell me, and I do pay attention. Okay, let's. Has anybody online got any questions? Okay, so there's a question about the extra credit for the last project. Each project has some extra credit potential associated with it. For the last one, if you do the extra credit component, you get 10% extra credit for that project. So it's not for the whole class. So anyways, everybody's hearing me. Any questions online about the survey? I think there's like a 20-second delay here. We'll come back to that a little bit later. Okay, so what I want to do now is talk in detail about the Q-Learning project. And as I go through describing it, if a question occurs to you while I'm describing it, please raise your hand here in person, and I'll stop and delve into that part. Or online, we'll check on you guys every now and then. Okay, so part one is implementing the Q-Learner, and let me talk about that by taking a look at the actual code. It's a little bit bigger. Oh, I guess I have to screen share so that the online people can see. Okay, so online people are asking about Dyna. We'll definitely talk about that. So if you unzip the zip file that goes along with this project, you get qlearner.py. me make that text a little bigger. Try to make it big so people can see here. You get qlearner.py, test qlearner.py, and a subdirectory TestWorlds. Now, it's your job to implement qlearner.py. Now, I provide some code that's kind of a template for that, and that code, if you use it just as is, will correctly work with TestLearner. So to test your code, we run TestLearner. qlearner.py will correctly respond to that, but it just chooses random actions. But your job is to fill that in with the correct code. So let me show you what that template looks like. A lot of questions about, what are the parameters coming in and coming out? What are their types and what should they be? Is I think fully answered if you just take a look at this example code. So your constructor should accept all these factors, and these are the numbers that were distributed with the code are the numbers that we'll use. I've actually fiddled around with some different numbers here, but in particular, I've tried different values of the probability of randomly choosing an action. But you should use the numbers that are distributed with the code there. But these are the parameters that your qlearner needs to accept. So how many states are there? How many actions are there? What's the learning rate? What's the discount rate? RAR is the probability of choosing a random action. So it's random action rate is what it stands for. RADR is random action decay rate. So what that means is after each step, we multiply RAR by 0.99. So after the first step, it'll go down to 0.4999 and so on. Pay careful attention to verbose. When we're testing your code, we're going to set verbose to false, and that means shut up. Okay. Sorry if I scared you there, but what it means is don't print anything. If you do print something, your code is going to take longer to run. So if verbose is set to false, be sure not to print anything. But when you're testing your code, you should set it to true and print stuff to help debug what you're doing. This parameter dyna is how many dyna updates you should do for each real update. Okay. Let me go to query first, and then I'll go back to query set state. So what query should do is it accepts the new state, S prime, and R, the reward for what you just did. And it should update the Q table based on that information and return an action. So my implementation, all that it does is it selects a random action and returns it. You should, of course, implement the stuff where you update the Q table and choose an action according to the Q table. There's also the potential for a random action. So you should look at RAR, and based on that value, choose a random action and return that random action. So that's what query does. Let me pause for a second and see if anybody's got questions about these functions so far. Okay, let's see if we got any questions from people online. There we go. Okay, do we have any questions? Still just the question about Dyna. I'll get to the Dyna question shortly. Okay. There's one part missing, which is query SetState, and the reason we need that is when we first start the iteration or the epoch, you don't know what your initial state is. So what SetState does is it says, this is your state, and oh, by the way, give me an action back. So what query SetState does is it should save that state. So here you can see I save that state S. It should also consult the Q table to find out what the best action is and return that. And of course, with some probability, choose a random action. So that's there's essentially just 3 methods here that you need to implement, and that's it for this project. Now note, we're going to test your code with a navigation problem that I'm going to show you in a moment. But there's nothing in here, there's nothing in this code about a navigation problem. This is a generic QLearner. It doesn't know that it's being used for navigation. It doesn't know if it's being used for trading stocks. It's just a generic QLearner. Now, the other part of the code that I'm going to show you in a moment converts this navigation problem and turns it into a reinforcement learning problem. But that's not code that you have to write. So I've seen on Piazza lots of people talking about how to convert the position of the robot into a state, and so on and so forth. You don't have to do that. That happens automatically for you. Okay. Let me show you what the navigation problem looks like. When you unzip, you get a couple test worlds. I'm actually going to create a bunch more, and I'll announce when I've created them. But I'll have at least 10 test worlds here for you, and I'm going to post the my solutions to the test worlds up on the wiki. But let's look at one test world, see what it looks like. It's a very simple CSV file. 0 means it's an empty cell, empty space. 2 is the initial location of the robot. 1 is an obstacle. And 3 is the goal. So the robot essentially wakes up. It's told its state. Well, the QLearner is informed about its state, which is this location. The QLearner should return an action, and then TestLearner says, "Okay, that's your action. I'll move you there. Here's your reward, and here's your new state." And that cycle repeats and repeats and repeats and repeats. And the code is set up so that each time the robot takes an action, it gets a reward of -1 until it finally touches the goal, and then it gets a reward of +1. So does anybody have questions about what the maps are like? They're all 10 by 10, so there's 100 possible states, 4 actions, north, east, south, west. I'm going to edit my TestLearner code a little bit so it prints more stuff. So test learner, for the most part, is code you don't have to worry about. Of course, you probably want to fiddle with it. For instance, here it says which world we're trying to solve and so on. But what I want to do here is do some more printing. Set verbose to true here. Okay, so you can see along the bottom there is what the map looks like. The asterisk is where the robot is right now, and X is the goal. And so we initialized the Q table to be random values between -1 and 1, and now the robot really has no guidance on where it ought to go. Because Q table is random, it's also choosing some random directions. So it's not very effective at this stage. You can see here printing some things out. The state is was 45 a second ago, and here you can see the actions it selected and what the reward was. And here I'm printing out what the current Q value is. So let me speed that up a little bit. Got a sleep statement in there that slows it down so you can see what's going on. I'll remove that. So it's going to go now for, well, while it's going, let me tell you what's going on. So it's constantly calling query of the Q learner, and the Q learner returns, here's my action. So test learner moves it accordingly, updates the state, and then queries again with the new state and the reward. When it touches the goal, it gives it then a reward of +1. So that's its final accomplishment is to give a reward of +1 when it touches the goal. Then the test learner brings it back to the original location. It uses query SetState to do that and lets it go again. And as you can see, now it's very effective in getting to the goal. So over 99 iterations, it converges to a solution that gets it to the goal in 24 steps. I think it can be done in 15 steps. Let's see, 1, 2, 3, and then we've got 10 going up here. So 13, 14, 15. Seems like you might need 16 is the very smallest number that you can do it in. Okay, so does that make sense to everybody so far? Let's see if we've got any online questions. Online people, you're slackers. Okay, any on-campus questions? All right, so we're gonna test your solution across 10 test cases. We're gonna take the number of steps that our reference solution took to solve it. And your program should solve it in less than 1.5 times that. So you should be able to solve this maze, for instance, in 36 steps. Then we're going to turn on Dyna, and we expect that you'll be able to accomplish it not necessarily in fewer steps, but that you will converge to a smaller number more quickly. So for instance, after say 500 steps with Dyna, you might very likely have already converged to the optimal solution. Okay. So now we have some questions online. Oh no, it's the same ones, but I missed this one. Do all 16 states in the path get the reward? Every time, so one thing to emphasize, the reward is not for being in a state. The reward is for being in a state and taking an action. So, as an example, when the robot was in this cell next to the goal, and it took the step to go to the goal, that's when it got the reward. So there's 3 different states around the goal from which you get a reward of +1. So if you're below it and you go north into it, you get a reward of +1. If you're to the east and you go into it, and if you're to the west, you go into it. The reward is not for being in the goal state, it's for moving into it. And similarly, for all the other states, every time the robot moves, it gets a reward of -1. Every time it returns an action, it gets a reward of -1, except for that last action that carries it over the goal. Okay, so there's a question now about Dyna. So let's talk about Dyna. Let's look back at that code. So when you implement Dyna, the thing that happens here is that within your query method, you need to hallucinate, or simulate is, I think, the more correct term. You need to simulate a bunch of experiences with the world. So let's go down to query. So what happens here is that right now, the only way that the Q-learner can learn is when it's called, when query is called, and it does one update to the Q table. Each time it gets called, it's one update to the Q table. So if over one epoch, what I call an iteration, let me change my code back so you can see what I'm talking about. Okay, each time you see the robot move here, that's one call to query. The robot, or the Q-learner, right now can only learn or update its Q table upon each one of these calls to query. Now, if we turn Dyna on, what happens is upon each call to query, the query function additionally does some number of additional updates. 100, 200, whatever, it might even be thousands. And those updates cause its policy to converge much, much more quickly. But the thing to keep in mind is we're still calling query, once every step. So from the outside point of view, we count how many times we call query, and that's kind of the measure of the cost of the at least one measure of the cost of the learner. Okay, so let's go back to this. So you need to implement some additional code within query that does these, that makes these updates to the Q table. So let me review how that happens. Let's start by assuming that you have T. Okay, so I'm going to use VI here to instead of a whiteboard, so I can write something. Let me not do that. Okay, so let's suppose we have T, and remember T is indexed by state, action, next state. So what that represents, and let me restate it clearly, it's the probability that if I'm in state S and I take action A, that I will end up in state S prime. So if we were to take the sum over all S primes for a particular state in action, it should sum to 1. Now, in our particular environment, in our particular world, the correct, if you had the correct Q table, it would essentially be mostly zeros and occasional ones, because if you're in a particular cell and you take a particular action, the probability is 1 that you'll end up in that next state. There's no chance that you'll end up in some other spot. When you're up against an obstacle and you try to take the action of going into the obstacle again, the test learner doesn't let you. So let's say this is state 55 and you say go north. Well, the test learner says, okay, you're still in state 55. So the transition T, the transition matrix would show T 55, comma north 55 is equal to 1, and all other values of for state there are 0. But that's just this particular environment. In most real environments, there is some probability that you're not going to end up in just exactly one other state. You may, if you try to go forward, you may end up a little bit over here, you may end up a little bit over there, or if you're buying or selling stocks, it's not necessarily going to go up exactly 1%, it might go down 0.2%. So this T usually is not exactly zeros and ones everywhere. But does everybody get what T is? Okay, so let's suppose you have T. Let me also suppose that you have R. I'm going to talk about how to get T and R in just a second. So R is the reward for being in state S and taking action A. Now, if you have these two, you can hallucinate an experience tuple. Hallucinate has 2 L's. Tuple. Okay. Okay. So how do you do that? So step 1 is randomly select an S. Step 2 is randomly select A. Now 3, you have to you have to find S prime, right? So consult T to find S prime. Okay, so let me ask one of you all how you would do that. So we have an S, we have an A. How do we find an S prime? Raise your hand if you've got an idea of how to do it. Yes, ma'am.
You generate a random number between 0 and 1 with an uniform distribution, and like according to that, you can check the probabilities for T and select an action.
Right. So let me repeat what she said. You generate a number, a random number between 0 and 1, and then using that random number, you can look at. So let me. So that is. We just call it R random. Okay. Okay, so find a random number between 0 and 1, and then looking at TSA, find S prime. So a way to do that, here's an easy way to do that, is so S and A are fixed, right? You've got this random number that you just drew between 0 and 1, and you just you do a for loop, and you accumulate the sum of the probabilities as you iterate over all the possible states here. And when that sum reaches the value of rand, boom, that's the action you select. Is that a reason? Okay. That's at least one way to speak more precisely. You should randomly select S prime according to the distribution. So one of those next states is going to be the most likely one. And so if you, in our case, there's going to be one of those states that has a value of 1, and if you draw randomly, you'll always pick that state. Okay, so it's important to understand this part before I go to the next part. Does everybody get this part? Explain it again. Okay, sure. Let me draw something on the board. For simplicity, let's assume that we have a small state space. Okay. Now we have set S and A. So I'm going to draw. I'm going to assume we have just 4 possible states here for the purpose of this argument. Okay, so I know it may be hard for those of you to see online. I'll just say what these are. So it's T SA0, T SA1, T SA2, and so on. So these are the 4 possible states that we might end up in after being in state S and taking action A. Now let me write down some probabilities here. So let's say for this one, the probability is 0.6. Let's say for this one it's 0, and we've got 0.2 and 0.2. Okay. So does everyone want to pause for a second to make sure everybody understands what I drew up here? One thing that we know is these numbers must sum to 1. Because with probability 1, we're going to end up somewhere, right, within our state space. Let's suppose, okay, so what we want to do is when we're in state S and we're looking at A, we want to, so this is a distribution. It's a distribution of probabilities. All distribution of probabilities means is, for each case, we have some number between 0 and 1 that indicates how likely it is to happen, and it must sum to 1. So what we want to do is randomly pull one of these states out of this distribution according to how likely they are. Is everybody following me so far? So what's the most likely next state? Uno, that's right, 1. Okay. Now I outlined a method for drawing from this distribution, and let me illustrate it. So somebody pick a random number between 0 and 1. I'll ask you.
0.72.
Huh?
0.72.
0.72? Okay. Sorry, you get to do the next one. Okay, so rand equals 0.72. So and let me do this. Okay, so what I'm going to do is show you this potential way of doing this. And the way of doing it is we'll step through this with a for loop, and we'll accumulate the sum of each of the probabilities. All right, so sum of 0 is 0. With 0.6, it's 0.6. With 0.2, it's now 0.8. And with another 0.2, it's 1.0. So I step through this one by one until that sum is greater than or equal to rand. So in this case, I would choose action 2. Now, if I were to throw the dice again, let's say I did that 100 times. Choose a random number between 0 and 1, and did this 100 times, and counted how many times I picked each one. I would have a bar chart that looks something like this. I never would pick state 0. I would pick state 1 about 60 times, state 2 about 20 times, and state 3 about 20 times. Does that make sense? So that's how, given a distribution, you can randomly choose a state from that distribution. Let's check on anybody online here. No new questions, okay. Okay, so yeah.
So how do you initialize T?
I haven't told you, but I will. So the question was, how do we get T, right? Okay, I'll do that in a second. Step 4 here is let R. So we need a little R, right? let R be big R of SA. So now we have SA, S prime, and R, and that's everything you need to update the Q table. Crap. Okay. Anyways, you'll just have to, we'll have to roll back the tape for you to know what that looks like. Okay. So with SA, S prime, R, update Q table. And you do this dyna times. That's the argument passed in, right? Okay, how do you get T? So let's do it in 2 steps. First step is, remember, your query function is being constantly called with the new state that you're in and the reward. You return an action to perform, right? And then you get a new state, right? So you can observe S, so that was the state you were last in. A, that's the action you last took. And S prime, which is the state that your query routine was just called with, right? So does everybody see where we get S, A, and S prime? Okay. So my suggestion is to create a new matrix. I'm going to call it TC for T count. And start up here a little bit above. Set all values of TC equal to a very low value, and you'll see why in a moment. Maybe you don't have to. I'm not sure, but anyways, we'll see in a minute. Okay. So this is in the constructor. Okay. In the query, you need to do the following. Okay, so you observe the last state I was in, the last action I took, and the new state. And all we do is we increment this count. So, plus 1. Okay, so we just count how many times that transition occurs, right? So assume we have these counts. Let me ask you this question. I'm sorry, this should be TC over here. So assume you have these counts, TC. How can you compute T from TC? In fact, we did this in the last lesson. So, so T, S, A, S prime is equal to what in terms of T count? Raise your hand and then you can speak loudly. Okay, go for it.
TC S A S prime divided by sum of TC S A code.
That is exactly right. All it is, a little applause in the back there, great. This is, and by the way, let's see. Wait, this is going to be 1, right? Oh yeah, that's duh. Okay, it's TC. That's what I'm messing up. This is the sum of all the times we've been in state S and took action A. And so we're summing it across all possible next states. So that's the sum of all the times we've been in that state and took action A. This is how many times we ended up in S prime. So if we just divide that by the other, boom, that's historically the probability that we end up in that state S prime. So this is how you calculate T. Any questions about that? Yeah.
But I don't understand when you calculate T. You calculate T before you start doing any.
Yeah. So the I filled it with very small number because I was concerned that in this division, the first time you let's say you've this is the first time you've been in state S and took action A. The first time you do this division, you'd have a divide by 0. If there probably is a more clever way to work around it.
But you update this T table every time the robot experiences a new change of state. So you have all the T table filled with 0 or epsilon
Right.
at the beginning, and then every time you take an action, you're updating it. But then when you hallucinate with Dyna, your hallucinations are.
So yeah, okay. So let me write some more pseudocode here. Okay, so this is within query. Okay, so we assume we have S prime R, right? Okay. So first thing we do is update Q table. I'm gonna, for now, not worry about generating an action. We want to update T, and we want to update R. I just showed how to update T. Let me show you real quick how to update R. R of SA is just equal to some alpha, alpha R. It's a weighted average of what it was before, plus the new reward we just got. That makes sense? Everybody get that for updating R? Okay. All right, so we update T, we update R, and I should say there's various more or less efficient ways of doing it, but let's just say we update TC of S prime. All that means is to increment it by 1, right? Okay, now now that we've got this additional increment there in T sub C, we need to update the appropriate probabilities, right? So you really only need to update the part of the world that where S and A are fixed. So you can just update those particular probabilities. Make sense? Okay. Now, for I in range 0 dyna, select random S and A, draw S prime from T, S, A. So now we have, and then we let R equal RSA. So now we have, we update our Q table with SA, S prime, R. We do that dyna times. And let me, in case I don't want to get in trouble, this is a subsection, this is the dyna part. We need to also throw dice randomly select action according to RAR, decay RAR. So it's just RAR equals RAR times RADR. We decay how frequently we choose random actions. Otherwise, choose action according to Q. Then we do our dyna part. And we return action. That's that's essentially the full outline of the query function. Okay, let's see if any online people have any questions. Would it be wrong to update RSA equals expected R according to SA? Sure. My method converges to that. I think in terms of for this particular problem, the navigation problem, here where I show you how to update R, I would just let alpha be 1, and it would fully believe the immediate rewards as soon as it gets them. Okay. I came in late. The link on the wiki says to pick the dyna SNA from previously seen states and actions. In those states, that what we're doing. Okay, I don't understand that question. Sorry. Okay, any other questions here on campus? Yeah.
So you're supposed to update the 2 table twice?
So you update it once here with the real information you get from the world, and then tens or hundreds of times here. Each time with one hallucinated experience. Yeah. Say it again. How do you initialize T? My suggestion is to initialize it with a very small number, all of them with the same value, like this. So the question online was how to initialize T, and my recommendation is with a very small number. Any other on-campus questions? That's a good point. So this you raise a good point. In that case, they don't sum to 1. In the way that we're using it, oh, you know what? I said TC. Excuse me. So that's the count. If you then compute T from TC, you'll get uniform probability for everything. The reason I initialized TC to this, okay, so let me back up again. So your earlier, I lied a little bit, your earlier question. So the first question was how do we initialize T? The correct answer is initialize T count to this small value. Then you can compute T from that count, and it'll end up with uniform probabilities everywhere. Any other on-campus questions? Okay. Yes.
So you pay RNR or you choose to run that fashion.
I'm sorry. Say it again.
So you pay RNR or you choose to run fashion.
We're talking about Dyna.
Yes.
Oh, choosing a random action. Okay. So the question is, what about this choosing a random action thing? So RAR is random action rate, and you should each time query is called with probability RAR choose a random action. You should also each time query is called slightly reduce that value according to this decay rate, RADR, random action decay rate.
Only when I'm choosing random action.
Every time.
And also in the Dyna part, do we choose a random action in the Dyna part?
No. Well, actually, yes, you choose a random action within Dyna on each iteration, but you choose a random action with probability 1 on each Dyna iteration, but you should not. Dyna has nothing to do with RAR. RAR is about choosing a random action to take in the real world. Any other on-campus questions? Yeah.
Otherwise, choose action. Like, what is the condition that we're checking?
What's the condition of what?
So in the first part, when you update the table, then you throw a dice randomly, select action according to R, decay RAR, and then otherwise choose action according to T.
Yeah. So you that otherwise is with regard to throwing the dice. So. So with probability RAR, do something random. Otherwise, consult the Q table. Okay. I've got to run. I can't do my normal lingering around and talking to people because I've got a WebEx I have to be on in 5 minutes. However, if you do have some questions, I'll be in my office and available probably at about 3:30. So I'm in this building room 316. So if you want to talk to me 3:30 to 4-ish, I'll be there if you want to talk to me some more. Sorry I can't normally hang out, but I've enjoyed having you all in my class, and hope to see you around campus. Have a great winter. Bye bye.